So let's look at ionic bonding first. And let's draw Lewis symbols for potassium and chlorine. So the Lewis symbol is just the element symbol with dots for electrons. So potassium is K and chlorine is Cl. So how many valence electrons does potassium have? 1. Remember, main group elements, the number of valence electrons is their group number. 1A, 2A, 3A, those guys. So I'm going to put 1 dot. So that's the Lewis symbol for potassium. It's real fancy, isn't it? How many valence electrons does chlorine have? 7. So when we put the 7 dots around, we want to pay attention to the sides, top, bottom, right, and left. It doesn't matter exactly where you put them, but you don't want to do this. 1, 2, 3, 4, 5, 6, 7. Okay, no circles here. We want to go top, bottom, right, and left. So 1, 2, 3, 4, 5, 6, 7. If it gets 8, it'll have 2 on each side, and it's really easy to see. So we know that potassium is a metal, and it's going to be relatively easy to get rid of this electron. So in chemistry land, I envision potassium going around saying, hey, I got this 1 extra electron, I need to ditch it, I need to get rid of it. And chlorine saying, oh man, if I had 1 more electron, I would be so cool. I'd be like argon, he's just like the bomb, I want to be like argon. Could you give me an electron, please? And here's potassium trying to get rid of an electron. And they're like, hey, we can work this out, right? So potassium transfers his 1 valence electron to chlorine. So let's move that over here. Nice. Now chlorine, doesn't that look nice, all complete and everything, 2 on each side? But chlorine has a charge now, right? What's the charge? -1, because it gained a negative charge. These negatives get pesky. So it's got a negative charge. That negative sign can kind of get lost in the dots. And so what we do is we put brackets around this, and we put the charge on the outside. Does potassium have a charge now that it lost an electron? Sure it does. It's a positive 1. So now we have a positive ion and a negative ion, and now they're very attracted to each other, and they're going to form an ionic compound. And this is going to be more stable than the potassium and the chlorine alone, and that's why it forms in the first place. Now, potassium ion, how many valence electrons does it have? Well, if we look at this, it looks like it has none, right? Here's the electron configuration for potassium. So this is the valence electron, right? It lost that valence electron. Now, with this one being gone, what are the valence electrons? It's still the electrons in the highest level that has electrons. The valence shell is now the third shell. So now it has this octet from the lower level. That's why potassium is good with losing an electron, because he peels that extra thing off the outside, and underneath it's all beautiful and full. We don't draw those dots in the Lewis structure because it would be really confusing if we had dots appearing out of nowhere. When we draw a Lewis structure, we'll move electrons around, but we're not going to bring any up that were formerly core electrons. And so the cations we'll see will often have no dots at all. And we just understand, oh, they lost the outer layer, the underlayer is always full. Any questions? So let's predict the formula for the compound that forms between magnesium and nitrogen using Lewis symbols. I know we learned to do this just from kind of wrote things on the periodic table, right? Let's do it with Lewis structures. Well, magnesium. So here's magnesium. How many valence electrons does magnesium have? What group is it in? 2. Normally what we do is we'll put the dots around by themselves first and then pair them up if we need to. So there's magnesium. And nitrogen, how many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. Okay, I forgot. I was going to do magnesium in a different color. It's a little trippy. I'm teaching the same thing in my 3A class right now. And so I kind of get this almost deja vu thing going on. Okay, so there's magnesium. So they're going to question.
So the right way to draw the dots is you put one on each side first?
Generally, you put one on each side first. There's sometimes where you pair them up, like for helium, but most of the time not. So I think generally it's safest to put them around one at a time and pair them up as you need. We're not going to get super hung up on that, though. So here's magnesium. What does magnesium want to do? He wants to lose 2 electrons. And see, electrons don't come out of nowhere and they can't disappear, right? And that's what I think is nice about the Lewis theory, is you see where are those electrons going. There's no electron bank where nitrogen can go and say, I'd like to make a withdrawal, please. And magnesium can't take these 2 electrons to the pound and say, I'm done with them, you take them. He has to find somebody to give them to. And so here's nitrogen wanting how many electrons? He needs 3, right? He needs to pair these up. He needs 1, 2, 3, and magnesium's got 2. And we're like, okay, well, let's see what we can do here, right? So we'll take these 2 electrons from magnesium and give them to nitrogen. That didn't work out very well. Now, what's the charge on magnesium? 2+. Is magnesium happy in a stable electron state? Yeah, because it's got 8 valence electrons, the next lower shell. Is nitrogen happy? No, he's closer. He's got 7 now instead of 5. Not happy. So magnesium's good. He's just going to hang out. Where there's 1 magnesium atom, there's probably some more. So nitrogen is going to look around for another magnesium atom who's nearby, who also has 2 valence electrons. This magnesium is also looking to unload 2 electrons, and the nitrogen says, hey, can I have one of those? And magnesium says, sure, you can have 2. And he says, no, I only want 1. Well, okay, that's better than nothing. What's really strange to me is I can talk like that for atoms, but I could not do this playing Hot Wheels with my sons. I don't know what's wrong with me. Now, is the nitrogen happy? Yeah, he's good. What charge does this nitrogen have? Say it louder. 3 minus, right? It gained 3 electrons. That's why I wanted to use a different color. It gained 3 electrons, and so it has a 3 minus charge. It's good. Is this magnesium happy? No. Well, if there was 1 nitrogen atom, there's probably another one. So enter another nitrogen atom. This nitrogen atom also has 5 valence electrons. He's looking to gain 3 electrons. This magnesium now has 1 it needs to get rid of. So he'll take that 1 and give it to the nitrogen. And the magnesium's like, oh, that's so much better. It's like this magnesium atom went to school and mom made him wear a hat and an ugly sweater, right? And he just wants to take them off so that he can look cool. If he unloads those 2 electrons, his energy lowers. That's the scientific explanation. So magnesium's good. How about this nitrogen? Is he happy? No. Does it seem like we're going to go on and on forever doing this? No, you guys are smarter. My 3A students are like, yeah, this is never going to end. No, it's going to end. What's going to happen? We need one more magnesium. So here's another magnesium with 2 valence electrons. And you guys get it. So these 2 electrons are going to go over here. And then that nitrogen is going to have an octet. Magnesium has a 2+ charge. The nitrogen has a 3- charge. But now we've seen where the electrons went and where they came from, right? This is why the formula is Mg123N2. So the formula, which is what we were getting at for the answer, Mg3N2. And the whole crisscrossing charges and stuff is nice, but it doesn't really explain what's going on. Does this make sense? It's always nice when you can draw pictures. So let's think a little more about the energy involved. I said this is going to happen because the energy gets lowered. What's happening exactly with that energy? We observe that the formation of ionic compounds is usually quite exothermic. And I've shown you pictures before of sodium metal reacting with chlorine gas to form sodium chloride table salt. It's highly exothermic. It will evolve 411 kilojoules of energy per mole of sodium. That's a lot. Well, where's that energy coming from? Well, in this process, sodium atom is becoming an ion. That involves an ionization energy. That first ionization energy for sodium is plus 496 kilojoules. So you have to put 496 kilojoules of energy in to get that electron off of the sodium. And if we look at the electron affinity for chlorine, this is going to offset that, but not completely. That's only going to evolve 349 kilojoules of energy. And if we add these together, we see that just looking at the transfer of an electron from sodium to chlorine, that should actually absorb 147 kilojoules per mole. It should be endothermic, and yet we observe that it's exothermic. So what's going on? It's the lattice energy. Lattice energy is the energy associated when you form a crystalline lattice of ions from those ions in their gaseous states. The coming together of those positive and negative charges releases a tremendous amount of energy. So I like talking about atoms as if they're little people and that they want to do this and they want to do that. It's really important to understand. The formation of ionic compounds is not exothermic because the metal wants to lose electrons and the nonmetal wants to gain electrons. That's not why it forms. There is a large amount of heat released when the cation and the anion coalesce to form a lattice. The transfer of the electron is actually an endothermic process. It requires an input of energy from the outside. But once you form those ions, then the force of attraction, pulling them together, that's going to release a lot of energy, and that's why the thing happens at all. Any questions about that? We can talk about them wanting to do stuff, but we have to understand that that's not actually why they're doing it. So here's an illustration of what's going on with that. If you're starting with sodium ions and chloride ions in the gas state, and those come together to form sodium chloride, the energy that's given off when that happens is the lattice energy. So here we've got all these ions, they're floating around as a gas, and as they come together and form a solid, a lot of heat is released. And that's the driving force for the reaction. Well, how do we figure out what the lattice energy is? The easiest way is to calculate it using what's called a Born-Haber cycle. This is a hypothetical series of steps, of reactions that represent forming that ionic compound from its elements. And this is going to use Hess's law. Remember Hess's law? you can combine different reactions, and if the sum of those reactions gives you the desired equation that you're trying to look at, you can add up the delta H's and get the end result. Because it's a state function, it doesn't depend on the path. So we use Hess's law, and we're going to choose steps where we know the standard heat of formation for each of the steps. And then we can add them up and figure out what's going on. We also need to know the overall change in enthalpy. So let's look at this. Like, wow, all of that, yeah. So down here we have sodium chloride solid. Here's enthalpy increasing as we go up. So if we're talking about forming sodium chloride, here's sodium metal and chlorine gas. This is where we're actually starting, and this is where we're actually ending up. All of this is imaginary. We're thinking about it. We don't actually do any of this. We observe that what am I looking at? It's always challenging to orient oneself. This is the heat of formation for forming sodium chloride from sodium and chlorine. And what we're going to do is we want to figure out what the lattice energy is, because what we said earlier is just looking at ionization energies, it should actually go up in energy instead of down. So if we take the sodium and go from sodium solid to sodium in the gas state, we know the heat of the formation for that. And that's going to require an input of energy. And then we're going to take this chlorine molecule and we're going to make it into chlorine atoms. And we can look up the energy required for that. And then we're going to take these sodium atoms and we're going to ionize them. And we know the energy required for that. And then taking this chlorine atom and making a chloride ion. This, now we're starting to come down because that was exothermic. The electron affinity for chlorine is negative. And so now we're at this point, the sodium ions and the chloride ions. When those come together to form sodium chloride, that change in energy is the heat of the lattice energy, the energy that gets released because of forming the lattice. If we can measure this step and all of these other steps, this is the one we don't know. You can't really just measure a lattice energy. There's just not really a way to do it. But we know that the sum of all of these other things has to equal this. And that's the easiest way to calculate a lattice energy. Does that make any sense? So we're imagining, well, if we went this step and this step and this step and this step and then to here, we know all of the other steps except this one that we're missing. Well, lattice energies have some trends. And one of the things that affects the lattice energy is the size of the ions. Let's look at the lattice energies here for lithium chloride, sodium chloride, potassium chloride, cesium chloride. There's a difference here. The lithium chloride has a larger lattice energy than the cesium chloride. And this has to do with the size of the ions. Over here, we've got an illustration showing the different sizes. All of these are making a compound with chloride, so that part is the same. But here we have the different ions, and as we go down the column in the periodic table, the size of the ions gets larger. Well, lattice energy is going to depend on how close the ions are in the lattice, and this gets back to Coulomb's law. The energy is proportional to 1 over the radius, the distance between the two things that are being attracted. So lithium, being a smaller ion, can get closer to chlorine. And here the distance between them is 241 picometers. As the ion gets larger and larger, the distance gets smaller. Cesium and chloride can't get closer than 348 picometers because they're big and bulky. And so the force of interaction is limited. It's like the magnet on the refrigerator. You put one piece of paper and it's fine. You put two pieces of paper and it's fine. You put three pieces of paper, and now if you slam the door too hard, the magnet starts to fall off. And you keep adding pieces of paper, and now it won't stick anymore because the distance is getting larger. It's a very small difference, but it makes a big change. So lithium chloride has a higher lattice energy because lithium is smaller. So smaller ions are going to have a larger lattice energy because they can get closer to each other. We also see a trend with ion charge. So let's compare sodium fluoride and calcium oxide. And we're comparing these because of similar sizes. So this one has a bond length of 231 picometers. This one's 239. Very similar. Based on a trend in atomic size, we would expect these lattice energies to be the same. But we see that the lattice energy for calcium oxide is much larger. And that's because the attraction energy also depends on the charges. Coulomb's law says that the energy is proportional to the charge of the first one times the charge of the second one. Well, here we have Q is +1 and Q is -1. We have +2 and -2. And so then we're expecting this to be like 4 times as large. And look at that. That is roughly 4 times as large. So lattice energy depends on magnitude of charge. Higher charges, larger lattice energy. That make sense? So here's a summary of the trends. Lattice energies become less exothermic with increasing ionic radius. As the ions get larger, the lattice energy goes down, becomes less. And the lattice energies become larger with increasing charge, more exothermic with increasing magnitude of charge. So let's predict some lattice energies. I put the periodic table up there so we can look at it. So we're looking at lithium bromide, potassium iodide, and calcium oxide. And this is one of those problems that students often have quite a bit of trouble with on an exam because you're like, what's going on here? You kind of have to pick it apart and say, okay, what are the two things that affect the lattice energy that I can look at for trends? We just talked about them. Charges and size. Well, what ions do we have in here? Lithium is +1 and bromide is -1. Potassium is +1, iodide is -1. Calcium is +2 and oxygen is -2. So here we have higher charges. Higher charges, 2 times 2 compared to 1 times 1. This is going to be roughly 4 times just based on the charge. So looking at the charge, which is the largest lattice energy? This one. So we're thinking this is probably the highest. Let's do it like this. So we're going increasing order of magnitude. So this will be the highest, and then we have 2 others over here. So lithium bromide and potassium iodide. We need to find these guys in the periodic table and compare their sizes. So here's lithium, and here's potassium. Who's smaller, lithium or potassium? Lithium, thank you. Lithium is smaller. And then let's look over here at the anions, bromide and iodide, which is smaller? The bromide, right? Size increases as you go down. So bromide is smaller and lithium is smaller. So lithium bromide compared to potassium iodide, their charges are the same, but these are smaller. So we're going to expect that this has higher or lower lattice energy. Are they going to stick together better? Yes, because they can get closer. Now what about So this is more than the potassium. So we're going to put this in here and then make sure that we don't have any other conflicting information. Because we can't completely disregard the size of these guys. I mean, the charge is a big deal, but size is important too. Potassium and calcium are similar in size. Oxygen is going to be smaller than the bromide and the iodide. And so the size here is probably going to kind of offset in comparing these two, the sizes are probably going to be kind of similar. So that would be the order. Wasn't the best explanation. Any questions? We're looking for size trends and charge trends. If you think about Coulomb's law, the energy is proportional to Q1, Q2 over R. Difference in charges here, like this, where these guys, Q1, Q2, would equal 1, and this would equal 4. That's a big deal. That's a fourfold change. So then the radius is probably not going to change enough to offset that. If these were much, much larger than these, then that would offset the difference in the charge. But these are not much, much larger. The calcium is about the same size as the potassium, and the oxygen is smaller. And so comparing this guy to, say, the lithium bromide or the potassium iodide, the size change is not real significant, but the charge change is huge, times 4. And then comparing these two, we're going to look at size. Now, if they gave you lithium iodide and potassium bromide, where one ion is bigger and one ion is smaller, then things get ugly. But I won't do that to you. Any questions? Models are awesome, but if models don't match up with reality, then they're worthless. Does this ionic bonding model explain observed properties of ionic compounds? We observe that ionic compounds have high melting points. Salt does not melt easily. Does this Lewis model explain that? Well, it does. Non-directional bonds. In a lattice of sodium and chloride ions, each ion is attracted in all directions by the neighboring ions. And so there's a force of attraction between a chloride ion and the sodium ion above, below, right, left, front, and back. So we have attractions in all directions. In order for this to melt, and here we've got an illustration of it melting, you have to break those interactions all over the place. And so that's going to require a lot of energy. A lot of energy is going to mean a high melting point. So our model does explain high melting point. Ionic solids are non-conductive. Salt doesn't conduct electricity. Now, salt and water does, but salt by itself doesn't. This salt crystal has charged ions in it, but they are not free to move. In order to conduct electrical current, you have to have moving charges. There's no moving charges here, they're stuck. If you melt the salt, we do see conductivity, and that makes sense because in a liquid, you can melt salt. In a liquid, then the ions are free to move, and so this will conduct electricity. We also observe that solutions of ionic compounds are conductive. Over here, we add salt to the water, and the light bulb goes on. Conductivity. Because as these ions dissolve in the water, then they become free to move, and they can move from one electrode to the other and conduct the electrical current. So the model explains reality.